So today's lesson we'll be talking about what are some applications or what are some things we can do with the cross product of two vectors. Now, as stated yesterday, you can do a lot of things with them. We're only going to stick to the basic mathematical, basic algebra slash geometric applications of the cross product because again, this is not a physics class, it's not an engineering class. So one thing you can do with cross products is to find areas of uh, particular shapes, in this case parallelograms, and by extension triangles. Triangles, after all, are just half of parallelograms. How is that possible? Well, I first want to recap yesterday's lesson. So the idea of a cross product is that if you have two vectors that have the same initial point, say this vector here and then this vector here, then the cross product will always be a vector that is perpendicular to both. Now it turns out, so this is the cross product here. Now what we did yesterday, among other things, was we found the magnitude of that vector, and we did it basically old school, right? We found the cross product, got the vector in component form, and then we just applied the magnitude formula. Magnitude of any vector is the square root of the x component squared plus the y component squared, and since we're in 3 space, you add the z component squared. But it turns out that there is an alternative way to find magnitude of a vector. So let's actually write that out. Yesterday, we found the cross product, and to find its magnitude or length, we used the formula that the magnitude of any three-dimensional vector is the square root of the x component squared plus the y component squared plus the z component squared. Well, what today's going to talk about is there's actually another formula to find the magnitude of a vector, or the cross product, or in other words, the length of the cross product. The length of the cross product may also be found if you know the following pieces of information: the magnitude of u, symbolically that, the magnitude of vector v, symbolically that, the angle between both vectors, symbolically theta. In other words, let's call this u, v. If you have these two pieces of information, if you know the exact length of these two vectors and you know the exact angle between them, then you don't need to do the cross product. You can immediately know what the length of this guy by a particular formula. So this length here, right? So let's call this u cross v. So the length of the cross product may also be found if you know those 3 bullet points by the following formula. The magnitude of u cross v is equal to the magnitude of u times the magnitude of v times sine of theta. Right? So you can sort of think of this as the alternative formula for the magnitude of the cross product. Now, I will admit that this is a nicer formula. It saves you the hassle of doing the cross product. It saves you the hassle of either memorizing that weird, complicated formula, or it saves you the hassle of finding the determinant. But you know what? again, when you're dealing with vectors in life, you may not be given these pieces of information. You may not know exactly what the angle between these two vectors are, which is not a hard computation, right? But then it starts getting too cumbersome. Oh, first you got to find the magnitudes of each vector. Then you got to find the angle between them. Then you got to plug it into this formula. It's sometimes, the shorter, the seemingly easier path that ends up being the longer path. Personally, if I was given two vectors and I was asked to find the length of the magnitude, I'd just do what we did yesterday. I would just find the cross product and then just use the magnitude formula. So why am I bringing this up? Well, this is important to know because sometimes you might need it, but it has farther implications than just finding the length of the cross product. Let's actually take a look at this visually. Right? What exactly does u times the magnitude of u times the magnitude of v sine of the angle between them really look like? Well, recall that. So what? Recall that two vectors may define a parallelogram. After all, that's how we added vectors back in 9.1, old school, geometrically, the tail-to-tip method. Right? So if I had two vectors, say, I don't know, vector u here and vector v here, I can always create a parallelogram by adding the other vector to the terminal point. So for example, I could add vector u at the end of v. Ooh, that's not a straight line. Or I could, it'd be nice if I made it the same length. Or I can add vector v to the end of u, and it creates a parallelogram. Well, the magnitude of u and magnitude of v are pretty obvious. Visually, this length is the magnitude of u. Visually, this length is the magnitude of v. But it's the magnitude of v attached to the sine of theta that's very interesting. Remember when we did magnitude of anything times the cosine of theta, that was the horizontal component. Well, magnitude times sine of theta is the y, or the vertical component. Now, since we are at a shifted axes, we have two vectors here, this right here is actually the perpendicular component on u. Right? Remember how u cosine theta was the component of u onto v? Well, if you swap out the u and the v and swap up the cosine for the sine, then it becomes the perpendicular component onto u. Visually, in other words, it is, let me use a different color. That is magnitude of v sine theta. And again, we're probably going, so what? Well, take a look at the formula for the length of the cross product. It's magnitude of u, and I'm going to color code this, times v sine theta. In our picture, it's this length here, magnitude of u, times v sine theta, which is this length here. Notice what we're doing. That precise quantity, magnitude of u times v sine theta, yellow times pink, is a base of a parallelogram times the perpendicular height. That is the precise formula for the area of a parallelogram. So that's a pretty neat implication. It turns out that while the cross product, conceptually is simply a perpendicular vector, its length just so happens to be the exact area of the parallelogram formed by those two vectors. It's such a neat idea. I'll say it again. The cross product of two vectors is a third vector that happens to be perpendicular to both of them. But more special than that, if you were to take a measuring tape and measure that length, that number itself, is going to equal the number that represents the area of the parallelogram that those two vectors make. Let's go ahead and write it up formally. It's a pretty neat and helpful way of finding areas of parallelograms. So instead of breaking in a protractor measuring angles, if you can describe the side lengths of a parallelogram as vectors, you can quickly find the area of it. So the area of a parallelogram. The length, it turns out, so the idea is that the length of the cross product of u and v symbolically looks like this, is equal to the area of the parallelogram formed by vector u and v. So if you ever had to find the area of a parallelogram defined by two vectors, you just do the cross product and find the magnitude. So it's a very simple thing to apply. So the questions will be very, very straightforward. For example, they could ask you to find the area of the parallelogram determined by vector u, which is, I don't know, 1, -1, 1, and vector v, which is determined by 1, 1, -1. Let's just make it all ones, make the numbers easy. I hope this works out nicely. And if it doesn't, then I picked wrong numbers. Let's go ahead and do this. Now, here's the idea. For area of the parallelogram, I need to find the length of the cross product. I got two choices. I could use this new formula that we developed, but that requires me to find the magnitudes of each vector. Not so hard. Find the angle between them, a little bit of work, but not so hard, and then do this whole multiplication. Not hard, but very tedious. Instead, let's just use the idea that the length or the magnitude of the cross product is the same thing as the area of the parallelogram. So that's all we're going to do. We're going to find u cross v, which should be easy. That's what we did yesterday. I like the matrix approach. You can use the straight up formula approach if you want. So that's vector I with -1, 1, 1, -1. Oh man, that's going to give me 0. Let's hope this is not all zeros. If it's all zeros, I might have to pick a different example, because if it's all zeros, it's not very interesting to see. J, so what's that? That's 1, 1, 1, -1. Okay, good, it's not all zeros. Plus K, and what's that? 1, -1, 1, 1. Is that all zeros? No, good. Okay. So that's going to be 1 minus 1 is 0. So I'll go ahead and write 0j. I know anything times 0i. I know anything times 0 is 0, but let's go ahead and write this for emphasis. And this is -1 minus 1 is -2, but I have the extra minus, so it's plus 2j. And then for the k's is 1 minus a -1, which is 2 plus 2k. Right? Or in other words, 0 to 2, if you like. But that's not the answer. So all we did was we found the cross product. But since it wants the area of the parallelogram, the idea, again, the theory is the length or the magnitude of this guy is the area. So all I have to do is find the magnitude. So the magnitude of u cross v is the square root of the x component squared plus the y component squared plus the z component squared. So it's the square root of 8, which is 2, squared to 2. So that was easy peasy. That's the area of the parallelogram formed by those two vectors. So again, it's hard to draw 3D, but if you were to draw these guys out in 3D and make the parallelogram and compute the area the old school way, I can bet money that it equals that. The only way I can make this harder, just like with yesterday, is if I don't give you the parallelogram, if I don't give you the vectors, I just give you like 3 points. Well, what did you guys do yesterday? You had to create your own vectors and do the cross product then. So it's the same idea as yesterday. So they may not be as nice by giving you the vectors. You would have to form your own vectors. Also, they may not ask you to find the area of a parallelogram. They might ask you to find the area of a triangle, but note the area of a triangle is 1/2 area of a parallelogram. Right? You should be able to see that. If I draw a parallelogram, if I split this guy in half and make a triangle, obviously the area is half as much. Or if I split it this way, the area is half as much. So that should be pretty simple and straightforward, I hope. So if I switch up the instructions a little bit, I hope you guys understand it's not a brand new concept. You just have to tweak your thought process and tweak your mathematical work. So, for example, if I asked you, find the area of triangle PQR, where point P is 3, -2, 6, point Q is -1, -4, -6, and I don't know why I put colons there. And point R is 3, 4, 6. So just like with yesterday, we need to create two vectors. It really doesn't matter what vectors we create as long as they have the same initial point. So I'll do my standard P to Q and P to R. So I'm going to call vector U vector PQ. So what is that? From 3 to -1 is -4. From -2 to negative is -2. And that is -12. I'll call vector V from P to R. So that is none for the x's. You added 6 for the y's, and you didn't do anything for the z's. So that's nice. Therefore, if I do the cross product, so that is going to be I, J, K, -4, -2, -12, 0, 6, 0. So that is -2, -12, 6, 0. -4, -12, 0, 0. I like all these zeros. That's nice. Makes it easy. And K is -4, -2, 0, 6. So for the I, so that's 0 minus a -72, so it's a positive 72. For the J's, it's 0 and 0, so I'll write the 0 just so it's there. And for the K, it's -26 minus 0, so it's obviously -26, so it should be a -20, or 24, excuse me, 24K. Okay. So now I have to find the magnitude. So it's the square root of the x component squared plus the y component squared plus the z component squared. And I'm going to need a calculator for this. Let me grab my calculator. So 72 squared plus 24 squared is 5760. Geez, let's see if I can definitely reduce it by 100. No, I can't. So 56, let's see. So I know that this is 8 times, I know I can divide out a 9 there. 9 times 8 times 10. So all I did was I just grabbed my calculator and started dividing by, I guess it's perfect squares. I don't know why I did 8s. I think I was thinking of perfect cubes, but it still works in our advantage. So I know that this is going to be an 8 and a 3, so that's what, 24? Yeah, I can pull out 24, right? So that's a 24 square root of 10. Right. 8 times 3, yep. Okay, so what did we do here? We found the length or the magnitude of the cross product. So this answer here is actually the area of the parallelogram. And that would be our answer if it asked for a parallelogram. But since it asked for the area of a triangle, all you got to do is split it in half, right? So all of this work, hence area of triangle PQR is 1/2 of that answer, which is 12 squared of 10. So that is just one application of the cross product. If you find the length of the cross product, you're actually finding the area of the parallelogram formed by the two vectors. If you were to slash the length in half, congratulations, you found the area of the triangle formed by the two vectors. So one neat application of cross product.